Hello, students. Have you ever wondered how mathematicians quickly figure out if a large system of equations has a unique solution? That's exactly where the fascinating world of determinants comes into play. Today, we are going to explore two essential concepts in determinants: minors and cofactors. Think of minors as simplifying complex problems into smaller, manageable pieces. Specifically, a minor is the determinant we get when we remove one entire row and one entire column from a larger determinant. To make this clear, let's consider a determinant with elements 1, 2, 3 in the first row, 4, 5, 6 in the second row, and 7, 8, 9 in the third row. If we want the minor of element 6, which is in the second row and third column, we delete that row and column, leaving us with a smaller determinant consisting of 1, 2 in the first row and 7, 8 in the second row. Simple, isn't it? Let's now apply this knowledge practically. Suppose we have a determinant with elements 1, -2 in the first row and 4, 3 in the second row. The minor of the first element, 1, is obtained by deleting its row and column, leaving us just the number 3. Similarly, the minor of -2 is 4, the minor of 4 is -2, and the minor of 3 is 1. See how minors simplify our work by reducing larger determinants into smaller parts? Easy, isn't it? Now, let's take a step further and talk about cofactors. Cofactors bring in a sign rule to the minors, and this small twist makes determinant calculations structured and simpler. Mathematically, the cofactor of an element aij is the minor mij multiplied by -1 raised to the power I plus j. To put it simply, if the sum of row and column numbers, that is I plus j, is even, the cofactor remains the same as the minor. If it's odd, we change its sign. For instance, going back to our previous determinant example, the cofactor of element -2, which is at position first row second column, becomes -1 raised to power 1 plus 2 multiplied by 4. Since 1 plus 2 is 3, an odd number, the cofactor becomes -4. To understand clearly, let's revisit our 2x2 determinant with first row elements 1, -2, and second row elements 4, 3. Here, the cofactor of element 1 is 3, since position 1, 1 is even. Cofactor of -2 is -4, since position 1, 2 is odd. Cofactor of 4 is +2, since position 2, 1 is odd, changing the minor from -2 to +2. And finally, the cofactor of 3 remains 1, position 2, 2 is even. Using cofactors simplifies calculations significantly when we expand determinants. Now, how do cofactors practically help us? Cofactors allow us to expand determinants along any row or column. This method is called cofactor expansion. Let's illustrate this with a 3x3 determinant. Consider the determinant having elements 2, 3, 5 in the first row, -6, 0, 4 in the second row, and 1, -5, 7 in the third row. If we expand this determinant along the first row, the determinant equals the first element, 2, times its cofactor, plus the second element, 3, times its cofactor, plus the third element, 5, times its cofactor. Each of these cofactors is found by calculating their respective minors and applying the sign rule we just learned. Clearly, cofactors provide a systematic way of solving complex determinants. There's another powerful property of cofactors you must know. If you take the elements of one row and multiply them by the cofactors of another row, their sum will always equal 0. This property greatly simplifies proving many mathematical results and solving equations involving determinants. For instance, in our earlier determinant with elements 2, 3, 5 in the first row, -6, 0, 4 in the second row, and 1, -5, 7 in the third row, the sum of products of elements from row 1 and cofactors from row 3 will be exactly 0. Such properties make determinants invaluable tools in algebra. Alright, let's quickly recap what we've learned today. Minors simplify determinants by reducing their size. Cofactors add a critical sign convention to these minors, providing structure for determinant expansions. Expanding determinants using cofactors gives us a practical and organized method for calculations, and the special properties of cofactors help solve equations systematically. And that's the foundation of how we compute determinants using the cofactor method. In the next video, we will explore how to use these cofactors and minors to find the adjoint and inverse of matrices, making solving equations even easier. See you there.